And here in chapter 8, we are going to talk about bonding. Now, this discussion of bonding that we are going to have in chapter 8 here concerns some things that we've already seen in the previous couple of chapters. And we're just going to kind of put them together to try to get a much more broad sense of why electrons behave the way that they do. So we're going to start off with this. Let's define what a bond is. By definition, a chemical bond is a force that is holding two atoms together in a molecule or in a compound. So it is literally some kind of action that is pushing these two atoms together. And what we know about that force is that it is related to electrons. Now, when it comes to bonding, there are two primary types of chemical bonds. There are your ionic bonds. Ionic bonds we've previously discussed. Form as a level of attraction between positive and negative ion. And then there are covalent bonds. These are attractions between shared electrons and the nuclei of those atoms. So in calcium carbonate here up top, I've got these calcium atoms that are shown here in gray. I've got these carbonate ions that are shown here as these red and black molecules. And they are attracted to each other by the opposite force of those electric charges. Positive attracts negative. In our second panel, we've got carbon dioxide. Carbon dioxide, the carbon and the oxygen are attracted to each other based upon the electrons that they share between the carbon atom and the oxygen atom. Now, there is a third type of bonding. It's not mentioned here. It's called metallic bonding. You saw a little bit about metallic bonding in the lab video that you had to watch. Metallic bonding exists in metals only. And it's a very specific type of bond where we have metal atoms attracted to this large group of electrons that have all been donated by all of the other atoms in the metallic sample. That's what gives metals some of their kind of unique properties. But let's compare ionic and covalent, because they are the two primary types of bonds that we look at. In ionic compounds, we find that the ions are held together by these forces of positive and negative charged ions. In the example over here, we have the calcium ion, Ca+2, and the carbonate ion, CO3-2. And it's the +2 charge of the calcium and the -2 charge of the carbonate that hold together this substance. And because there is such a collection of charge, what we see in ionic compounds is this kind of thing. Structuring, crystal making arrays of bonds, not just one atom to another. In molecular compounds, we see sharing of electrons taking place. So I've got shared electrons between that carbon and that oxygen. I've got shared electrons between that carbon and that oxygen. That sharing of electrons keeps the carbon and oxygens together to make carbon dioxide. But you can see there's not a whole lot of interaction between the molecules and each other. One of the main reasons why, there's no charges. We have nothing to hold those atoms to each other, at least from one molecule to another. Whereas this positive charge on the calcium not only attracts the negative charge of that carbonate, but it can attract that negative, that negative, that negative, and so on, and vice versa. So let's look at ionic bonds a little bit more closely. Ionic bonds are created by attractions between opposite charged ions. So I've got a positive charge attracting a negative charge. I got a negative charge attracting a positive charge, and so on. Ionic bonds tend to occur between metals and nonmetals, and they do so in the following way. The electrons in the cation, which is usually the metal, give away their electrons to the nonmetal to form an anion. So my metal ions tend to be my cations. My nonmetal ions tend to be anions. And electrons are going from the metal to the nonmetal in order to make those ions in the first place. So if I have sodium and chlorine, right now, both of those are neutral atoms. But if sodium gives an electron to the chlorine, two things happen simultaneously. The sodium, having lost an electron, now has a positive charge. The chlorine, having now gained an electron, has a negative charge. And the two charges, since they are opposite in each other, cause those ions to attract each other as a result. And so that's what's going on with ionic bonding. And again, the charges that are made attract more than just the one ion. We can see in this figure 8.7 here, there are multiple attractive forces between the cations and the anions. There are also repulsive forces between the cations and themselves, the anions and themselves. The reason why the crystal forms is because the attractive forces are far more strong than the repulsive forces are. There are way more attractive forces than there are repulsive forces. And as a result, those increased attractions keep that crystal together much more so than they would staying apart. Covalent bonds, on the other hand, these are bonds created by sharing electrons. And in sharing these electrons, we're going to see no electron transfers, but rather electron sharing going on. Now, this tends to occur between nonmetals, and we'll get into the why in a little bit here. Electron sharing is a lot more personalized than electron transfer. It's a lot less attractive as a result. So the net that we get here, we get weaker bonds overall. And we get few or no interactions between the molecules themselves. So again, big difference between ionic and covalent is how those molecules interact with each other. Covalent molecules really don't interact with each other at all. All of that sharing occurs between two atoms in the molecule. Whereas in an ionic compound, I form these ions, and yes, there is a definitive attraction between this positive and this negative where the electron transfer took place. But this positive also attracts a whole bunch of other negatives. And this negative also attracts a whole bunch of other positives. It's more than just those two interacting. Now, overall, what does this mean? How do these kinds of interactions impact what we observe about ionic compounds versus covalent? Well, we can see there's a pretty stark difference. Ionic compounds tend to always be crystalline, solid. As crystalline solids, they tend to have high melting points, high boiling points. Covalent compounds, on the other hand, because there isn't a whole lot of interaction between the molecules, they tend to have lower melting points, lower boiling points. And as a result, we tend to see them in all three phases. So ionic compounds almost exclusively are solids. There are a few exceptions, but almost exclusively they're solid. Covalent compounds, very weak interactions, low melting, low boiling. The solids that they do make tend to be soft, tend to be waxy. So think about sulfur. If you've ever seen just plain elemental sulfur, it's kind of like a yellow sandy powder, very soft to the touch. Phosphorus, very similar, very soft to the touch. You know, even ice. Take an ice cube. Hard, but not so hard that you can't really do anything to it. If you put an ice cube in your mouth and you crunch on it, you can break through it with your teeth. If you took a similar sized crystal of salt and did the same thing, you might be able to do it, but it would take considerable more force to do so. Covalent compounds tend to be very poor conductors of heat and electricity. You saw this in lab last week. You did the conductivity tests. Think about, how did ammonia do? How did sugar do? How did acetic acid do? How did plain water do when you held it up to that conductivity apparatus? The answer in almost all those cases was, well, either it doesn't conduct electricity or it conducts electricity very weakly. Contrast that to your ionic compounds. Their electrical conductivity is quite high. Put them in solution, they conduct electricity quite well. Get them to melt, at a high enough temperature, you would see that they would conduct electricity also. The last point, solubility. Ionic compounds tend to be soluble in water. That is a property that we will call polarity. Water is considered a polar solvent. Carbon tetrachloride, CCl4, is considered a non-polar solvent. And so what we can see is that ionic crystals tend to dissolve in water, which means they have polarity. They are polar. They tend not to dissolve in carbon tetrachloride, which means that they are not nonpolar. And the opposite is true for covalent compounds. Most covalent compounds are lousy in water and pretty good in nonpolar solvents. There are some exceptions in there. Obviously, the sugar that you dealt with would be polar. Methanol and other small alcohols are polar as well. But most of your covalent compounds do not qualify in this kind of way, which is good because most of the covalent compounds that we encounter are things that we don't want to dissolve in water, like ourselves. Most of what makes up you is covalent compounds. Those covalent compounds and their inability to dissolve in water makes it so that you can exist on cloudy, rainy days and not have to worry about dissolving away. So, based on everything that we've discussed in an identification sense, let's try to identify the types of bonding in each of these substances. So our first one, NaF, sodium fluoride. Is this an ionic compound or a covalent compound? Gotta go back to the beginning. How do I identify an ionic compound? What am I looking for? Well, it's not gonna be two metals. If I have two metals, that's a metallic bond. I'm looking for a metal and a non-metal. I've got sodium, which is a metal. I've got fluorine, which is a non-metal. Metal and non-metal. This is an ionic compound. All right, second one, ClO2. Is chlorine a metal? No. Is oxygen a metal? No. Here I've got two nonmetals, so I'm talking about a covalent compound. Number 3, FeSO4. Fe is the element iron. Is iron a metal or a nonmetal? It's a metal. So I've got a metal, SO4, sulfur, and oxygen are both nonmetals. We recognize SO4 as the sulfate ion. This is iron 2 sulfate, in fact. This is an ionic compound. SO2, sulfur is a nonmetal. Oxygen is a nonmetal. I've got two nonmetals. This is covalent. CaClO2 taken twice. I've got calcium. Calcium is a metal. ClO2 -1, the chlorite ion. This is calcium chlorite. This is an ionic compound. So in identification, all we're really looking for is these markers. Can I identify, okay, this compound's got a metal and a nonmetal. This compound's got two nonmetals. This compound is, well, it's not a compound. It's just a bunch of metal atoms together. That's what I need to do to identify a substance based on its bonding. But now we get to the real heart of the matter. We know that bonding exists, but we really don't know why things bond. Now, to answer the question of bonding, we're going to have to answer the question of non-bonding. Because if we cannot figure out why some things do not bond, it might give us some insight as to why things bond in the first place. So we know our noble gases, neon, xenon, argon, radon, these elements do not bond. They are chemically inert unless under really, really dire circumstances. But really, they're the only ones that act this way. What makes them so special? Why do they lack bonding characteristics when others have some ways of bonding in general? And the answer to that question comes back to the idea of valence electrons. We talked about valence electrons in the last chapter. Remember, there are two different kinds of electrons. There are the core electrons. These are the ones that are in the inner energy levels, the ones closest to the nucleus. And because they are so close to the nucleus, they do not interact with anything other than each other and the nucleus. So they aren't involved in bonding. But in addition to those core electrons, we have valence electrons. And valence electrons are in that outermost energy level. They are further away from the nucleus. And because of their distance from the nucleus, they are actually able to interact with other atoms. And in their interactions with other atoms, they go out and make chemical bonds. So when it comes to explorations of bonding, we really don't care about those core electrons. What we care about is those valence electrons. How many are there? And what kinds of things do they do? So we talked about this in our last lecture. How do we know how many valence electrons there are? Again, it comes back to the periodic table. Going based off of our group number, and again, depending upon whether you're using the IUPAC system, where you just take the group number, and if it is double digit, you subtract 10 from it. Or if you've got one of those CAS numbering systems with the A's and the B's, you look at the Roman numeral next to the A, and that tells you how many valence electrons there are. So for the halogens, which we find in group 7A or group 17, we would expect 7 valence electrons. For the alkali metals in group 1, we'd expect 1 valence electron. For the noble gases in group 18 or group 8A, we have 8 valence electrons. And all this was stuff that we talked about on Monday. Now we start to piece together the full picture. If our noble gases, which have 8 valence electrons, do not react, and all of the other ones with all of the other different kinds of valence electrons do, then there must be something about that number 8. And what we can get to, the main crux of the issue, bonding exists to get us to 8 valence electrons. So the noble gases already have 8. They don't bond because they already have what they need. Everything else bonds in some kind of way to get them to 8 electrons. If we look at it from that standpoint, we can understand why the alkali metals in group 1 and the halogens in group 17 are so reactive. In group 1, they have 1 extra valence electron. If they get rid of that electron, then they have the completely filled valence level of the energy level below it to fall back on. And that makes it stable. All they got to do is ditch that 1 electron. And for the halogens, they already have 7. If they add that 1 extra electron, that gets them to 8. So they're desperate to add that 1 electron. And that's why they're so reactive. So the alkali metals are desperate to ditch an electron. The halogens are desperate to gain an electron. And as a result, what do we see? Lots of compounds of alkali metals and halogens together. Sodium and fluorine, sodium and chlorine, sodium and iodine, potassium and bromine. You start running down your list of ionic compounds, and you see a lot of NAs, Ks, and LIs. You see a lot of FCLs and BRs and Is. That's because they're so close. They're right there. And they're much more reactive as a result. Now, we do have a methodology for helping us to keep track of all of this. It's called a Lewis dot symbol. What Lewis dot symbols do is they allow us to keep track of valence electrons, and they also allow us to keep track of how those electrons interact, how those electrons move to either create ions or to create covalent compounds. The rules for Lewis dots are simple. I'm going to draw a generic symbol right here. So let's say that we were taking the Lewis dot symbol for element X. So there's element X in the middle of my slide. Now, as far as valence electrons go, there are 4 possible places that I can put electrons around element X: on top, on bottom, and to the left and right. Why those locations? Well, again, we have to think about, what does that valence shell look like? In that valence shell, I've got an s orbital, and I've got the p sublevel that has 3 orbitals in total. 4 orbitals. And since electrons don't like each other, they're going to separate themselves out amongst those 4 orbitals as far as possible, which is why we don't see any doubling up of dots until all 4 of those zones are filled up first. So element X is going to have 1 dot for every valence electron that is present in that element. And those dots are going to spread themselves out as far apart as possible. And that's going to give us our idea as to what is going on around this element. So to that end, I can look at something like, okay, if I have 3 electrons, then element X has 3 electron dots around its symbol, just like that. Without the little circles.
Does it always start in one area?
That part, that doesn't actually matter. So where you put the dots is somewhat arbitrary. So long as they are separated from each other, you can put them on in any order. The important part is that they stay separated until they have to pair up. So let's do, to that point, let's do some examples here. So if I'm looking at lithium, lithium Li is in group 1. It's an alkali metal. So it's only going to have 1 electron dot. Now, where you put that electron dot, left, right, top, or bottom, doesn't matter. What matters is that we show that lithium has 1 electron dot. And for aluminum, aluminum is in group 13, so it's got 3 valence electrons. Again, it doesn't matter where I put them, so long as those 3 dots are apart from each other. If you gave me one of these, this would be incorrect. The dots don't pair up until they have to. But where that empty space is really doesn't matter. For oxygen, oxygen is in group 16, 6 valence electrons. And so again, doesn't matter where, my first 4 dots have to be separate from each other. My next 2 just need to be paired up in some kind of way. But again, where you've got that double dots, top right, left, or bottom, doesn't matter. For fluorine, I have 7 dots because it's a halogen. Again, where that unpaired dot is doesn't really make a difference. So now we have an idea of, a way to organize our thoughts with these Lewis dots. Let's get into the principles of bonding. We know that atoms will do whatever is necessary to get to those 8 electrons. They can do it by sharing electrons, which we'll talk about. That'll be primary topic of Friday. We can also see it in the forming of ions by either gaining electrons or by giving electrons away. Again, our general trends, metals and nonmetals, tend to go the transfer route. where a metal gives its electrons away to the nonmetal. Nonmetals tend to go more in the direction of sharing. So overall, what does that look like? Well, let's start with ionic bonding. In ionic bonding, our metal atoms tend to have small numbers of valence electrons. So for example, we have sodium, magnesium, aluminum. Sodium's got 1, magnesium's got 2, aluminum's got 3. When sodium forms an ion, it's going to give away that electron. The net result will be the sodium plus 1 ion because it gave away 1 electron. When the magnesium gives away its 2 electrons, it'll end up with a magnesium positive 2 ion because it gave away 2 electrons. When the aluminum gives away its 3 electrons, the net result will be the aluminum 3 plus ion because, again, it had to get rid of all 3 of those electrons. So now it is 3 electrons short of where it was. Nonmetals, on the other hand, since they have larger numbers of valence electrons, they tend to go in the opposite direction. So let's look at this again from a standpoint of some commons. So let's look at fluorine, oxygen, and nitrogen. Fluorine has 7 valence electrons. Oxygen has 6. Nitrogen has 5. In this case, electrons aren't leaving because, I mean, to get to where sodium was, fluorine would have to get rid of 7 electrons. That's pretty unlikely. What happens is we add an electron and we end up with fluorine minus that now has 8 electrons around it. We add 2 electrons to oxygen. We now have oxygen with a -2 charge and 8 valence electrons around it. We add 3 electrons to the nitrogen to make the nitride ion, N-3. But we now have 8 electrons around that guy. So in metals, metals tend to give away their valence electrons, and by vacating that outer shell, it's got the same kind of electrons that a noble gas does. It's got its octet that way. Nonmetals add electrons, and in adding electrons, they get to 8 electrons on the outside through those additions. They just have to absorb as many electrons as it takes to get there. Notice that the one group that we've really left out here is group 14, the carbon group. Why is that? Well, carbon's kind of stuck in the middle with 4 valence electrons. To do the things that metals do, it'd have to lose all 4 of them, which is not an easy task. But on the flip side, with those 4 electrons, they'd have to gain 4 more, and that's not exactly easy to do either. So what we see in that particular group is they're much more prone to sharing. The carbon group is going to be much more in the covalent camp than they are in the ionic camp. And that's why we don't see a whole lot of carbon and silicon-based ions and ionic compounds, unless they're a part of a polyatomic ion, like a carbonate ion or an oxalate ion, where they themselves actually aren't transferring electrons. What's happening in those is they are forming covalent compounds that have acquired extra charge. The extra charge is usually on the oxygens that they pick up and bond with, not on the carbon itself. When we look at covalent compounds, what we will see is that this is primarily a non-metallic kind of property. And it's going to be a sharing kind of proposition instead. So what we'll see in those kinds of cases is I have, for example, carbon and a bunch of hydrogens. And what can happen is each of the hydrogens, being that they are in group 1, have 1 valence electron. Carbon, being in group 14, has 4 valence electrons. And what happens is that these electrons effectively pair up. To make covalent compounds. Where each one of those lines here in the revised structure represents 2 shared electrons between the 2 atoms that they connect, which we would call a single bond. And so that's the big difference between the ionic and the covalent bonding. Again, ionic bonding, we're forming those ions by electrons being grabbed or given away. Covalent bonding, we're talking about, hey, I've got an unpaired dot and you've got an unpaired dot. Why don't we put them together and share them between us? So this is where we will pick up on Friday. We'll talk more about covalent bonding. I'll teach you how to draw simple structures like this one from the Lewis dots. And that'll pretty much effectively wrap up chapter 8 for us as well. So we're in the part of the semester. The chapters are going to get shorter and kind of choppier. So you're going to have more assignments because we are going through more chapters, but we're going to go through them a little bit more quickly. I'll see you on Friday.